Okay, well, maybe we'll get started for the second lecture of day one of the school. So I'm the lecturer, Louigi Addario-Berry. I'll give you a bit of course overview, nowhere near as well structured and organized as what JC did, partly because I realized in preparing my lectures that my course outline was overambitious, and so I've had to make adjustments. But let me tell you what my plans are at the moment. So I'll just share a screen from my tablet. Right, so please feel free to ask questions in the chat. I'll do my best to monitor the chat. So some of the topics which I mentioned lecturing about in the summary on the website included first passage percolation on trees, which is sort of secretly under another name, branching random walks. I mentioned lecturing about random minimum spanning trees. I mentioned lecturing about mixing times of interacting particle systems. And I do hope to cover this and this. There's a fair amount of background required for these, which makes it, I think, unrealistic to think that I'm going to get to this, just based on how many pages of notes the earlier topics are already seeming to consume. And in particular, for this topic, there's a fair amount of background that needs to be covered first. I'm getting a bit of feedback from someone. I'm wondering if I can just mute participants for the moment. Let me see. I'm going to mute all for now, if that's okay. Sorry about that. There are some topics which are quite mathematically interesting in their own right, but which also are necessary background for studying these later topics, which include topics with a less optimization flavor, so random trees and tree-like graphs. And so in particular, I want to tell you about both their local and global structure. And then closely related is mean field percolation, which also goes by the name Erdős-Rényi random graphs. Okay, and then sort of in the course of preparing, I realized that there's a set of techniques called spine techniques that kind of show up all throughout all of these topics, which are related to the question of the typical behavior of uniform samples of vertices within large random trees and graphs. And I couldn't resist adding to the set of topics something that wasn't in the list, which is branching processes with immigration. And its link with the Keston-Stigam theorem, which is a sort of slightly, just something that's just slightly beyond the scope of most sort of first courses in stochastic processes. It has a beautiful and fairly straightforward proof. It's about when the martingale limit for a branching process is non-trivial. And it isn't too much of a detour from the other topics. But given all of this material, I don't think that I'll be getting very much beyond there. And so some of the later topics that were mentioned in the introduction related to mixing times and Chen-Stein and things like that probably won't show up so much in the course. A sort of theme that's hiding behind a lot of modern probability is the concept of universality, which is the idea that so macroscopic behavior is insensitive to the precise microscopic details. So this manifests in the central limit theorem in the statement that centered and rescaled sums of random variables behave like Gaussians under only a mean zero variance one assumption. So that is, you saw that in the first lecture today, Jean-Christophe mentioning that a lot of the behavior in these spin models and glassy models, which he'll develop for Gaussian random weights, also holds for much broader classes of random weights. But in his lecture, he's focusing on Gaussians because there are some very nice, if you like, identities or algebraic tools, facts that hold for particular choices, such as Gaussian integration by parts, which allow you to tell the story in a cleaner way than when you want to do it more generally, when you have to use estimations and approximations. Okay, so in the same way that the Bernoulli central limit theorem can be solved using exact binomial formula and then a Stirling approximation, whereas when you pass to a general central limit theorem, you need another set of tools. In the setting of so random trees and tree-like graphs and mean field percolation, for example, and random minimum spanning trees, the story is most cleanly told when the underlying probability space is suitably uniform, when there's which gives you a nice algebraic structure where you can tell the story. But very large parts of the story I'm going to tell you extend either rigorously or conjecturally to much more general classes of models. And at some points, there are sort of open research directions, which one could follow by trying to build on these specific models to prove universal behavior of this kind. Okay, so I actually want to get into the math fairly quickly today, and then the math itself, I'm not going to go very quickly. We ran entrance polls for many of the students to get an idea of your background, and the background is quite varied. So for some of you, some of the beginning material will be fairly familiar. For others, it will be new. I can guarantee that the particular proofs I plan to present today are new because, as far as I know, they didn't exist a month ago. So even if the facts are known to you, then the ways of proving them should be somewhat interesting. Before I get to that, let me just mention a couple other things. So for students who are trying to follow along with the exercises, I set up a website where I have posted lists of sort of suggested exercises for each day. So that's, I'm going to post the link in the chat. And depending on how, so here's that page. It's a very minimalist page, just with sort of links back to the main summer school website, plus the list of exercises that seem relevant for the first week. And that for Friday, I might add one more exercise to that list. If at the end of today, my estimation of what's a reasonable set of exercises for a day is wildly off, then we'll recalibrate. But the main point is not to stress yourselves out by trying to do everything if that's unrealistic. It's to use the exercises to get a better, a deeper understanding and intuition for the math that I'm presenting. So, you know, do what you can and get what you can out of them. Occasionally there'll be an exercise which will essentially be me outsourcing a little bit of work to you where there's a fact I want to use in the course of a lecture that I don't want to prove, but those facts, I've tried to be quite certain that they're sort of small and believable things rather than anything that should make you really scratch your head for very long. Okay, maybe I'll just quickly sketch what my plan is for this week's lectures, which largely revolves around this first part of the very brief outline I just gave you. Oh, thank you. So there's a question from Connor in the chat, which is, which text are the exercises from again? So they're from the lecture notes that I've been writing. And those lecture notes will continue to develop. There's about 40 pages of notes or 45 pages right now. I hope that I'll find time while lecturing to also continue to expand them. I have various, that's my plan. Hopefully it'll work out. Any other questions about that background before I talk about what I'm going to do today and in this week? Okay, so my week one plan is basically to cover the following topics. So the local and global behavior of random labeled trees. Okay, so by local behavior, I really mean the graph structure near a typical vertex. And by the global behavior, I mean the distribution of distances between sort of finite sets of sampled vertices. I want to talk about large random graphs with boundedly many cycles. And I want to talk about line breaking constructions. And distributional properties. Random trees and graphs. So, so these line breaking constructions are, this is a technique to describing the limits of the scaling limits of large random graphs and trees, which are related to very nice distributional identities for sort of joint distributions of distances. And part of the story I'm going to tell you this week is how, in fact, such line breaking constructions already exist in the finite world. So before passing to the limit, I think I'll jump right in. So when I talk about random labeled trees here, what I really mean are let me already define a set. So I'll write Tn for the set of rooted trees with vertex set. The positive integers from 1 up to n. Okay, so so for me, right, a tree is, so that means that this is a connected acyclic graph. And saying it's a rooted tree means that there's a distinguished node, which I'll denote by rho, which is the root. Okay, so an example of a rooted tree might be something like this. Okay, so this would be this is a tree which is an element of the set of trees with vertex set from 1 up to 8. So that would be T8. And I've drawn the root here at the bottom. So this is rho of T is equal to 4. Okay, so so this is you know, in some sense, one of the most elementary kinds of probability you can do. It's the sort of combinatorial probability where you take some finite set and then you draw a uniformly random element of the set and ask, what does that element look like? Okay, so that's a sort of simple question. So what does a uniformly random element of Tn look like? And this is my notation for uniformly random sample. Okay, so whenever we have a finite set, if I use this element sub u of the set, that means draw a uniform sample. Okay. And finite probability, you know, relies on counting. So before, it's hard to answer the question of what a typical sample looks like if you don't know how likely or unlikely different things are. So if I draw something out and say, oh, it has this property, I want to know if that's likely or unlikely. Well, if I don't know how many things there are overall, it's hard to answer the question of how unlikely a given observation is. So, you know, a natural and important first step to understanding the probabilistic model is to do the combinatorics. So the combinatorics of this model is very well understood. So this is Cayley's formula. Says that the number of rooted labeled trees with vertex set 1 up to n is just n to the n minus 1. Okay, so this is a fact which many of you will have seen. Many of you may not have seen or may not remember. It depends on how much discrete math you did during your undergrads. It's a well-known and well-understood fact. So there's a paper by Moon, Canadian probabilist or combinatorialist. So AMS notes or bulletin article from 1967, which lists about 7 or 8 proofs. So well, I'll put my slides up. I've got a list, but it's long. There's proofs by Cayley, by Proofer, Clark, Rayleigh, Goebel, Moon himself, Kirchhoff, Polya. Okay, so those are some proofs from 50 or more years ago, and then more recently there are proofs by André Joyal. Has a beautiful proof using what are called vertebrates from 1981. That might be the prettiest proof that I know. There's a probabilistic proof by Jim Pittman, which is also very beautiful, and I've found useful in my own research from 1998. Remco van der Hofstede has a proof which proceeds by the analysis of Poisson branching processes, and that's a connection that we'll see and make use of in these lectures as well. That's from 2014. And the proof I want to tell you about is based on this line breaking construction. And this is, sorry, this is van der Hofstede here. This is so something that we found with Serta Donderwinkel, who's a doctoral student with Christina Goldschmidt and is attending these lectures. Hi, Serta. So just from this spring. Okay, and the nice thing about this proof, or a nice thing about this proof, is that it's actually going to sort of instantly give us access to some of the probabilistic properties that we're interested in studying for these trees. Okay, so let me explain how that works. And I think that maybe I'm going to start by drawing how the proof works, and then formalize a little, because I think the drawing is really quite clear. Then when I proceed to sort of give myself a bit of notation and formalism, you'll see you'll have a picture in your mind of what we're doing. So this is the proof via line breaking. This is n to the n minus 1. Okay, so what does the right-hand side here naturally count? It counts sequences, so of n minus 1 integers from 1 up to n. That's a very natural way to think about the right-hand side. And so how can we take such a sequence? Let me draw one down here. So 6, 1, 4, 4, 8, 10, 4, 6, 3. Okay, so I want to take a sequence like this, and I want to build a tree. And the way I'm going to do that is simply by reading from left to right, okay, and building the branches of the tree as I go. So the first thing I see will be the root, okay? And then the next thing I see is a 1, so I'm building a branch. The next thing I see is a 4, building a branch. Okay, and now when I see a repeated entry, like this second 4, what that means is that I have to go back and start growing a second branch. Okay, so the repetition is an instruction to start growing a new branch. Okay, if I just sort of stop here and start growing a new branch, then I have this dangling edge. And how do I deal with that? Well, I'm just going to turn that into a leaf of the tree that I'm building. Okay. And what's the rule? Well, the leaf needs a label, and I'll just use the smallest available label. So what are the available labels? They're the things that don't appear in this sequence. Okay, so in this example, the available labels, so let me say available leaf labels. So what doesn't appear in this sequence between, the sequence has length 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're building a tree on labels 1 up to 10, and the things that don't appear are 2 and 5 and 7 and 9. Okay, so here we're reading left to right, 6, 1, 4, a branch finishes, and so we use the first label 2. Okay, then we see the repetition, we start growing a new branch, 4, 8, 10, another repetition that says that we're going to go back at this point and start growing yet a third branch from 4, okay, but we need to first finish this branch by adding a leaf, and that will have label 5, okay. Now we start growing our third branch. Oh, we instantly see a repetition This 6 here has already appeared previously in the sequence, so that is a very short branch just of length 1. We need to terminate it with a leaf, so we use the leaf of label 7. And then our final branch 6, 3, and then the termination rule is always to add the last leaf at the end. So we add a leaf of label 9. Okay, so this is a procedure for taking a sequence and turning it into a tree just by reading left to right, building branches, and each time there's a repetition in the sequence, we view that as an instruction to start a new branch. Okay, and the branch that previously terminated terminates with a leaf, and the leaf label we use is just the smallest available label. Okay, so let me write that down a little bit more precisely. So if we're given a sequence of n-1 integers and n to the n-1, then we will let r be the number of repeated entries in the sequence. Okay, so that means an entry is repeated if it appears previously, so that's an I such that vi is equal to vj for some j less than I. Okay, and let's then list the repeated entries as, well, the indices of the repeated entries. As I1, I2, up to IR. Okay. So it's possible that there are no repeated entries, right? This is a sequence of n-1 values from 1 up to n. They could all be distinct. Okay. But what's guaranteed is that there are exactly r+1 values that do not appear in the sequence. Okay, because the sequence has only n-1 integers from 1 up to n. So if there are repetitions, then there are r+1 things missing. Okay, so the values that are missing we'll list as well. So not appearing in the sequence V as L1, L2, up to LR+1. So in this example, those values were 2, 5, 7, and 9. Okay, and then we just build a tree using these, using this information now. So it has root, which is just V1, the first entry of the sequence, and values. So the first branch will be from V1 up to VI1 minus 1, right? That's this part. And then the new leaf takes value is just, the first leaf is L1. And then the next branch will be, so VI1 up to VI2 minus 1. And then L2. Okay, that was this branch. Right, VI1 is a repetition by definition, so so that's a branch going off of a previously off of a previously introduced node and not a leaf, and then this continues. The last branch will be so VIR up to VN-1 followed by L, the last leaf, LR+1. Okay. So that's a sort of more formal description of this construction I just showed you. I can't resist showing you a small animation of this that my doctoral student Benoit Corsini made. I think it's quite lovely, and makes the inverse construction quite clear as well. So let me just share the bijection animation. So here's a tree with 10 vertices. The root is 6 here. Okay, so what's the remember the procedure that built this tree from a sequence? The first branch it built was a branch that started at the root, which is 6 here, and went to the smallest labeled leaf. So that's this leaf 2 here. Okay, so that's going to be the first branch. And in view of that, the sequence must have started 614 that this tree came from. Okay, and the next branch went to the next smallest labeled leaf. That's the 5 there. So the next branch is this 4, 8, 10, 5. Okay. Now the third branch goes to the smallest remaining leaf, the 7. So that's just 4, 7. You see each time in the sequence, we never write the leaf. We only write the other things on the branch that go to the leaf. Okay, and the final branch 6, 3, 9, we write down the 6 and the 3, and the 9 is reserved up top. Okay, and then here's the other direction of the bijection, which I just sketched, but it's obviously much nicer in this animation than in my handwritten notes. You just take the branch, grab the next available leaf label, and build your branch. Okay. So I'll just take a quick look at the chat. I see there's a question from Delphin. Is this new correspondence related to the Aldous-Broder algorithm in some way? We sort of thought that at some point, or I did. I don't know if Saoirse did, but it isn't. I mean, it seems very close, but so in the Aldous-Broder algorithm, at least the most direct connection would be Aldous-Broder algorithm run on the complete graph. So that's this procedure where you do a random walk, and the random walk builds a branch, and then when the random walk revisits the location that it's already seen, then you start building a new branch. But in that construction, when the random walk revisits a previously visited vertex, that first branch doesn't end at a leaf necessarily. The procedure can later go back and grow other stuff from that spot that it previously left. And so there's something, whereas in this procedure I just described, it's really fundamental to the process that each time you build a new branch, the spot where you end is a leaf and remains a leaf for the whole process. So that seems to be some distinction between this procedure and the Aldous-Broder algorithm. Okay, I'm just going to share my iPad screen again. Right. So so it's not clear to me if I even really need to formalize the inverse bijection, but I think I'll just write down quickly what the sort of what the symbols are that explain that animation that you just saw. So it won't take me long. Is the procedure clear? Are there any questions about the procedure itself? Okay, so so the way that you go from the tree back to the sequence is you just list the leaves of the tree in increasing order as L1 up to L R plus 1. So R is at least 0 here. There's any rooted tree has at least one leaf. And then we'll just build a sequence of trees. Okay, so, and the sequence of trees are really these branches. They're obtained by adding these branches one at a time. And then the branches are giving us the sequence of labels that we'll list down to get a sequence of n-1 labels in the end. So T naught is just the one vertex tree consisting of only the root. Okay, and then for each I from 1 up to r plus 1, we'll let pi be the path. So this will, so it'll be a branch of the tree, if you like. So this is the branch going from ti minus 1 to the next leaf li. Okay, and then we just let ti be the tree you get from ti minus 1 by adding the branch, the next branch. Okay, so so the first term here is always some vertex of the tree ti minus 1, and the last vertex along the branch is the leaf li. Okay, and then so these are the lists of vertices that we just string together to get a sequence in n to the n minus 1. So the sequence corresponding to t goes p1 up to, or rather p11 up to p1 h1 minus 1, and then p21 up to p2 h2 minus 1, all the way up to pr plus 1, 1, pr plus 1, hr plus 1 minus 1. Okay, so the fact that I'm stopping at h1 minus 1, h2 minus 1 here, and so on, this is precisely what you saw in the animation where the leaf doesn't get included in the sequence, it gets shunted off to the side. So you don't need those leaves in order to reconstruct the, or rather you can work out what those leaf labels are just by looking at the sequence. You don't need to record them. Okay. So I see a question, where do the sequences come from? So let me just, maybe I did leave myself space to do an example of this, of how these branches come about from the tree. So let's draw a tree. So I'm going to draw the leaves in a different color. So maybe we have this. This is a perfectly good tree, right? So what's the rule? I construct this sequence of trees and branches. So the first tree just has the root. This is my root row. Okay, and then so P1 has the labels along the branch to the smallest leaf. So that's this branch here from that goes 1, 2, 3, 7. Okay, 1, 2, 3, 7. P2 is the branch from that first tree, T1, to the next smallest leaf. So that just goes 2, 8. Okay, and I'll highlight the branches as I go so that we can keep track of where we're going at each step. So this now I've highlighted the tree T2, and the third branch P3 goes from T2 to the third leaf, which is this 9. So that goes 1, 6, 9. Okay, and now the final branch, you can see P4 is 3, 4, 5, 10. Okay, and so if you now to construct your sequence, what do? You just concatenate these lists, P1, P2, P3, P4, except you don't include the leaves. You don't include those final terms in each of the branches. So the sequence we get is 1, 2, 3. That's from here, and then 2 from P2, and then 1, 6 from P3, and then 3, 4, 5 from P4. Okay. So I hope that that explains the construction. So let's now, having seen this bijection, start to think about some of its probabilistic consequences. So I recommend, by the way, if you're not completely sure that you got it, just draw some trees, draw some sequences, and play around. It'll come quickly. Okay, so let me the first corollary I want to draw tells us about, or the first consequence of this that I want to describe is a sort of distributional identity for the distance from the root for a randomly sampled node. Okay, so let's let or a randomly sampled leaf. So if we take says we take a uniformly random tree with n vertices, and now let's let U be a uniformly random leaf of this tree T. Okay, and now so this is notation that I'll use later as well. So I'll write this sort of modulus or absolute value of U to mean the distance from the root to U. Okay, so for example, in this drawing, the modulus of 10 would be 1, 2, 3, 4, 5 here. The modulus of 8 would be 2. It's just the number of edges on the path. Okay, then now if I also let V be a uniformly random one of these sequences in n to the n minus 1, okay, and define I of V to be the index of the first repeated entry, right? So that's the first time VI where we see an entry that already appeared before in the sequence. Okay, then mod U plus 1 has the same distribution as I of V. Okay, so that's not hard to see using this bijection. Okay, so the bijection, the thing that it most easily tells us about, in fact, is the distance to the smallest labeled leaf. So let's let L be the smallest labeled leaf. Of T. Okay, and now this is one of the places where the uniformity of the model is very nice, because it doesn't matter whether we study a random leaf or the smallest labeled leaf, because the labels are uniform. So permuting the leaf labels doesn't change the distribution of the tree. Okay, so the distance, the height or the distance to the root for the smallest labeled leaf is the same as the distance to the root for a uniformly random leaf in distribution. Okay, but now for if we think about the sequence that we get by applying the bijection to this tree T, okay, well, T is uniformly random, and we just have exhibited a bijection between Tn and sequences in n to the n minus 1. So that means that that this sequence is indeed a uniformly random sample, a uniformly random sequence of length n minus 1 with entries from n. Okay, and so that's just a particular way of sampling this sequence by taking the tree and then applying the bijection. Okay, but when we build the sequence in that way, then the first repeated entry is precisely the distance to the first leaf plus 1, right? Because let's just think about that, right? The first repeated entry in the sequence, we go 1, 2, 3, and then the 2 repeats because that was where the branch ended. Okay, so you see here 1, 2, 3, 4, 4 vertices, 3 edges. That first repetition precisely corresponds to the number of vertices on the first branch. Okay, which is that distance, the number of edges plus 1. Okay, so we've shown that under this particular construction of the sequence, that index of the first repetition is exactly the height of the leaf plus one. And so in particular, that means that those two quantities have the same distribution. Okay, and we also said by this symmetry of permutation invariance that that height plus one, that looking at the smallest labeled leaf for a uniform leaf is equivalent. Okay, so that's a nice straightforward identity for the distribution of the distance to a random leaf in a Cayley tree, in a uniformly random labeled tree. Okay, and that fact in turn can be used to get sort of limiting asymptotics for the distance to a random leaf in a large random tree. Okay, so let me, in order to tell you that, let me say, let me introduce the Rayleigh distribution. So this is worth defining if you haven't seen it before. So the Rayleigh distribution, this is the probability distribution on the non-negative half line, defined by having density x e to the minus x squared over 2. Okay, so so another equivalently, so if x is Rayleigh distributed, then the probability x is greater than x is e to the minus x squared over 2 for x positive. Okay, so a second corollary of this proof is that if we take a uniformly random labeled tree and we let u be a uniformly random leaf, then so the height of u divided by n to the half converges in distribution to a Rayleigh. Okay, and this, you know, given the identity we've seen, is basically in the flavor of an exercise, because so we know that this is distributed as I of v minus 1. Okay, and so, and just I'm going to ignore sort of issues of rounding for a second. So what's the probability that this random leaf has height bigger than x root n? Okay, that's the same as the probability that I of v is bigger than x root n plus 1. Okay, and that's what is this asking here? This is asking for there to be no repetitions in the first x root n plus 1 entries of a sequence of random samples. Okay, so this says this is the probability that v1 up to v x root n plus 1 are all different. Okay, well, that's, I mean, for that to happen, first v2 has to be different from v1. That has probability n minus 1 over n. And then v3 has to be different from n1 from v1 and v2. That has probability n minus 2 over n, et cetera, et cetera. Okay, so this is just the product I from 0 up to x root n plus 1 of 1 minus I over n. Okay, and then a Taylor expansion shows that this converges to e to the minus x squared over 2. Okay, so this, this calculation here is developed a little bit in the exercises. In fact, so something that when we study the local structure, something that we'll see is that even though a random vertex of a random tree doesn't need to be a leaf, of course, typically random vertices are not too far from being leaves. So the subtree sort of, if I pick a random vertex and look up and see how many vertices sit above it in the tree, there'll typically only be a bounded number of such vertices. So you might guess then that that this behavior would also hold with a uniformly random leaf replaced by a uniformly random vertex. Indeed, that's true, and that is something that one could access, for example, well, that follows quite straightforwardly from the Aldous-Broder algorithm by a computation similar to this. Okay, so maybe this is a good point to pause. I'm going to, in the second part or the later part of the lecture, I'm going to present one more easy consequence of this bijection, probabilistic consequence of this bijection, and then talk about how the bijection extends to forests, because that'll be, it's very easy and it'll be useful for what comes next. But any questions now before we take a 3-minute break? I see there was a bit of question and answer already happening in the chat, which is great. I see 2 questions in the chat. One, can you explain again why the sequence corresponding to a tree is also uniformly distributed? Yeah, so, I mean, what this bijection, so what did we just do? We took the set Tn, right, which are these trees with vertex set 1 up to n, and we put them in bijective correspondence with sequences of n-1 integers from 1 up to n, right? So bijection means we've paired these up. One, each thing on one side is paired with exactly one thing on the other, right? So now that means if I pick a uniformly random tree over here and just look at the sequence it corresponds to, well, then I'm going to get a uniformly random sequence over here. That's just that's just saying the uniform distribution pushes forward under that map, precisely because the map is bijection. For the next question, how is the root of a tree chosen when encoding it as a sequence? It seems like we have more than one choice. Good. So indeed, there is more than one choice. Let's look again. That sort of, well, the choice is, the rule is that the root is, so did I? Yeah, I said here, the root is just the first integer in the sequence. So this sequence started with 6, so the root is 6. Okay, and going the other way, we indeed had, so when we started from the tree, right, and built the sequence, the first branch that we listed down starts at the root, which was 1, and we listed 1, 2, 3, 7. So and the sequence indeed starts with 1. Okay. So but on the other hand, if I decided in advance, I want a tree whose root is the label 1, I'm always going to root at the smallest labeled vertex, then I wouldn't need to record that first entry. Okay. And so then I could just delete that and I would still have all the information I needed. And then I'd have sequences of length n to the n minus 2. And Cayley's formula is sometimes stated with n to the n minus 2 and counting unrooted trees or equivalently trees where the root is specified in advance. Okay. Can you explain the last equality of the proof of the corollary? This one? This one. Right. So here the question is, if I take a sequence of, I guess maybe the one thing I can say is if I have a sequence which is uniformly distributed over sequences of length n minus 1 whose entries are all in n, I can equivalently say that each of the terms in the sequence is just a uniformly random sample from 1 up to n, and those terms are independent. Okay, so each of these entries is an independent sample from 1 up to n, and so for k of them to be different, this is just a birthday paradox. So you say you want the second one to be different from the first, the third to be different from the first two, the fourth to be different from the first three, and those are these terms showing up. Okay, so that's explained a little bit more in the notes if you want to go over it. I don't think I'll say much more about that live. But maybe I'll continue on now. Just mention the last probabilistic corollary I wanted to, and then talk about the extension to forests. So I guess before I state the next corollary, I need to tell you what I mean by, well, I just need a tiny bit of notation for the number of children of a node. So given given a tree, let's say in Tn, and a vertex of the tree, we'll write so CVT for the number of children of V in T. Okay, so I mean, for example, right, and for this tree T here, we would have C2T is 3, vertex 2 has 3 children, and C5T is 2. Okay, and so being a leaf is equivalent to saying that you have 0 children. Okay, and so then here's a very simple corollary. So if I let T be a uniformly random tree with labels 1 up to n, and let's say that Cn is just the number of children of the node with label 1 in Tn. Okay, so that would be 0 in this example because 1 is a leaf. Okay, but because over here the tree is random, this is a random variable. Okay, then Cn converges in distribution to a Poisson 1 random variable. Okay, and so the really nice the reason that this is super easy to prove with this bijection is that so using our bijection, okay, if I write so V for the sequence, so let me say, so if I fix a tree, a deterministic tree T and Tn, and I write v1 up to vn for the sequence v of t, okay, then for any, so I want to know, how can I look at the sequence and figure out the number of children of a given vertex of the tree? Okay, so I'm going to use the sequence to figure out how many children a given vertex has. Okay, so for any I in n, I claim that the number of children of I in t is just the number of times that I appears in the sequence v. So it's the number of j from 1 up to n minus 1 such that vj is equal to I. Okay, and to see why that's true, I think it's the simplest thing is just to go back and look at how the construction works. Okay, so remember, when we're building the tree from the sequence, each time we see a repetition, first of all, each time we see a number, we give that vertex a child, right? We see a 6, that means we're building a branch where we give 6 a child. And then each time we see a number again, we go back and start building another branch from that vertex, so we give it another child, right? So when we see 4 here, that gave 4 a child. When we see another 4, we started another branch growing from 4, so 4 got a second child. When 4 appeared a third time, we started growing a third branch from 4, it got a third child. Same with 6, right? 6, the first 6 gave 6 its first child, the second 6 gave 6 its second child. Okay? So just because each time a number appears, that means we start growing a branch from that vertex. That means the number of appearances of a given integer is the same as its number of children in the tree. Okay, and really, that's actually a statement that this bijection specializes to bijections for trees where you also say how many children you want each vertex to have. Okay, and lots of the bijections of Cayley's formula, in fact, have that property that they have sort of micro-canonical versions. They have versions where you're allowed to specify more data, and the bijection specializes to more sort of to a bunch of sub-bijections. Okay, but anyway, so that's why the number of appearances of a given integer in the sequence is the same as the number of children of that integer in the tree. Okay, and so now what is if I look at a sequence which is uniformly random in so this is the sequence v1 up to vn minus 1, a uniformly random sequence in n to the n minus 1, then what's the number of times that, so the number of j from 1 to n minus 1, such that vj is equal to 1? Okay, well, if I take a uniformly random sequence like this, then then each of these terms in this sequence is just equally likely to be any number from 1 up to n. Okay, so the first one has probability 1 over n of being 1, and the second one has probability 1 over n of being 1, and so on. Okay, so that means that the total number of appearances of 1 is just a binomial random variable, so with n minus 1 trials and success parameter 1 over n. Okay. And we know that this is, the bijection tells us, with using this observation, that the number of appearances of 1 is the same as the number of children, that this has the same distribution as our value Cn, the number of children of 1 in the random tree Tn. Okay, so Cn is distributed as this number of 1s. That's binomially distributed with this bin n minus 1 over n, and now the binomial approximation to the Poisson tells me that this converges to a Poisson 1 random variable. Okay, and so that's that step. I sort of expect you have seen in a grad probability course, but if you haven't, I mean, the way you prove that this converges in distribution to Poisson is just check that for each k, the probability that this equals k converges the probability of Poisson 1 equals k. That's a straightforward calculation. Okay. And so as an exercise, I'll leave you a slight extension of this corollary. So the corollary says that if I look at a randomly sampled node, then the number of children is asymptotically Poisson distributed. The exercise is to actually say that the whole empirical degree distribution converges to Poisson. So if I, so let me write pi n for the empirical degree distribution. Of Tn, so Tn is still this uniformly random tree. Okay, then so that what do I mean by that? I mean this is a probability measure, but it's a random probability measure. So it depends on the tree, and so it just says you can think of this as the probability measure you get by picking a random node and looking at how many children that node has. Okay, so that's a random. That distribution depends on the tree. So we write that as, so this is a Dirac mass at C. And then, so what's the probability, what probability do we want to assign to C? Well, it's just proportional to the number of nodes that have exactly C children. So the number of vertices of T such that 5, 9. Okay, so these are they're rooted, but they're unordered. It doesn't matter that I've drawn them left to right as 5, 9, 2, 3. I'm not counting. That's just an artifact of the way I drew it. This is the set that they belong to. Okay, is the definition of a labeled forest clear? Okay, so here's the last fact of the day. So for any integers k and n with n bigger than k, any set S of size k of integers from 1 up to n, then the number of forests on vertices 1 up to n with the root set S is just k times n to the n minus k minus 1. Okay. So if S has size 1, then this says that the number of forests with vertices 1 up to n, where I tell you in advance what the root should be, the one element of S, is just 1 times n to the n minus 1 minus 1, right? So that's n to the n minus 2. And that agrees with our previous Cayley's formula. Because in Cayley's formula, we got to choose the root, so there were n possibilities, and the answer was n to the n minus 1. If the root is specified in advance, then we lose a factor n, and we get n to the n minus 2. Okay. And so the proof of this shouldn't feel too bad if you sort of feel like you understood the proof of Cayley's formula. So we're going to do a similar proof. So if we're given a sequence, now the sequence is not going to have n minus 1 entries, but n minus k entries. Okay, and I'm going to insist that the first entry is an element of the root set S. Okay, then now we'll proceed as before. So we're going to build a forest, an element of FNS using such a sequence. So we'll say that an element VI is a repeated entry if there's some j less than I such that VI is the same as VJ, or if VI is in S. Okay, so the picture so what you should be thinking of here is that we know that we're going to build a forest with root set 2, 3, 5, and 9. Okay, so it's as though these roots are already there. They're already in our forest, and that means that if they appear in this sequence, they already count as repeated entries, even the first time they show up, because we know that they're going to be roots. Okay, so that's why there's this additional caveat here. And now so as before, we'll list the repeated entries. So we were using I for the indices of them, so VI1, VI2, up to VIR in increasing order. Okay, and now how many leaves are there going to be? Okay, so that's now again going to be R plus 1. So what are the leaves of our tree? They're the integer of our forests. They're the integers that don't appear in this sequence. Okay, like before, the integers that don't appear are leaves, but now also that aren't roots. Okay, so they're the integers in n minus s, which don't appear. In V. It's L1 up to LR plus 1. Okay, so is it still, as a sanity check, does it make sense that that if there are R repetitions, there would be R plus 1 things that don't appear? Well, yes, because there's, let's see. Or maybe I'd better do the construction to be sure. But the point is, no, this set here has, now, because there are k roots, this set has size n minus k. Okay, and the first term, is guaranteed to be an element of S. Okay, which leaves n minus k minus 1 terms. And so that, but our sequence has length, right, so we have n minus k minus 1 entries, and now this set has n minus k terms, so the number of repetitions must be one fewer than the number of things that don't appear. Okay, and now, and so then once you've sort of figured out where the repeated entries are and what your leaf set is, then you just build the branches of the forest in exactly the same way that we did in the proof of Cayley's formula. So now we use the same construction. As for Cayley's formula. Okay, so let's do an example of how that works. We'll build a forest with 12, with vertices 1 up to 12, and roots 1, 2, 3, and 4. And let's look at the sequence, which goes 3, 7, 6, 1, 2, 8, 1, 6. Okay. So what are the repetitions in this sequence? Well, okay, so we said that the sequence has to start with one of the roots, and it does. It starts with 3. Okay. And then the repetitions are the entries of index greater than 1, which are either already seen in the sequence or which are roots. So, so this is a repetition because 1 is a root. This is a repetition because 1 is a root, because 2 is a root. This is a repetition because 1 is a root. And this is a repetition because 6 actually already appeared in the sequence. Okay. And so that's, having figured out where the repetitions are, that tells us sort of what our branches are going to be. There's going to be one there, and then another one here, and then another one here, and then another one here, and then another one here. And now we need to work out what the leaves are. So what's missing from here? Well, there's no 4, but 4 is not a leaf because it's already a root, so it doesn't get counted. Okay, the things that are missing, the leaves, 5 is missing, 6, 7, 8 are all there, 9 is missing, 10 is missing, 11 is missing, and 12 is missing. Okay, and so now to build our forest, we know that the roots are 1, 2, 3, 4, and the first branch goes 3, 7, 6, and now we're about to start a new branch, so we have to terminate with a leaf, so we put the 5 in. Okay, and now we start our next branch from 1. We see we're instantly going to be starting another branch, but we need to add a leaf, so we'll put the 9 in. Okay, the next branch starts from 2, and it goes 2, 8. Now we're about to start another branch, but we need to put a leaf in, that's the 10. Okay, the next branch starts from 1 again. It immediately terminates, we need to put a leaf in, we put the 11. And now we start growing a branch from 6, and that's the last branch. It goes to the leaf labeled 12. Okay, so that's how the bijection works. Okay, and so the inverse bijection is really, you just build the branches. So the sequence of branches and list their entries, excluding leaves. To obtain a sequence v1 up to vn minus k with v1 is in S. Okay. So this construction is a bijection between what? Between forests with vertex set 1 up to n and the root set S, and sequences of length n minus k, but where, so almost all the entries are unrestricted except the first entry has to be an element of S. Okay? And so what does that tell us? It tells us that, so this bijection implies that the size of the forest FNS must be the same as the number of these sequences of n minus k entries whose first entry is in S. So that means there's k choices for the first entry. K, remember, was the size of S. Okay. And then there's n choices for each of the remaining n minus k minus 1 entries. So that's the number of choices for entries v2 up to vn minus k. Okay, so that's the proof of this generalization of Cayley's formula. And like Cayley's formula, this bijection for forests, specializes. If you wanted to say exactly how many vertices or which vertices had degree 2 and which had degree 5, then you would just only be allowed to use sequences where those numbers appeared the correct number of times. Okay, so that seems like a good point to wrap up for today. Tomorrow, I'll use this bijection to start to understand some other aspects of the local structure of uniformly random trees and forests, and then, time permitting, we might start to talk about the global structure as well. So that's linked for those who know some of these buzzwords to a Poisson-Galton-Watson tree condition to be infinite, or the sort of infinite spine construction. That's the local structure picture I want to tell you about. Any other questions about the math from today? I have a sort of more polished version of these. Well, in addition to the typed notes for this, which are already online, I have a more polished version of the slides, which I'll post as well. Someone asked if I could repost the link to the slide to the problems that I posted earlier. Yeah, there it is. Oh, Grigori beat me to it.